Okay, so I just got the prompt that we're live on YouTube as well. So welcome to everybody, those of you that are with us in the Zoom call, and those of you that are watching us through our live cast on YouTube. Okay, so I just got the prompt that we're live on YouTube. Hold on. So, welcome. There you go. I can hear myself on the live stream. So let me share that again. This is our second panel of next generation electrochemistry. And so I already give some of the introduction this morning. I'm not going to go through all the details again. You have some of the details in the slide. This panel is also, again, a research panel. And so remember that the research panels are meant to be a discussion between the members of the panel who are experts in the domain field that we're going to be focusing on. Each of them will give an opening statement, and if you saw it this morning, we're running around 5-10 minutes. The goal here is to do an opening salvo of what they see as the big fundamental questions that are that we face in the coming years in, again, the topic at hand. And we want to focus on questions that have to do with electrochemistry and research in electrochemistry. After that, we'll do discussion. There's about 40 students and postdocs in the Zoom call, and I will give the opportunity to have them come in live and throw questions at the panelists as we go, and that will be in addition to the discussion in the panel between the panelists themselves. There's some of you on YouTube, if you want to post questions, YouTube allows you to post a question in the chat, so we're monitoring that as well. We're going to be running for 90 minutes. Zoom doesn't kick us out, but I want to be respectful of everybody's time. This morning, we ran a couple of minutes above time or past time. So we'll target finishing in 90 minutes. If we are very excited about the discussion, we can always, if the panelists allow it, spend a few minutes beyond the 90-minute mark. For the faculty, if you were not there this morning, my charge to you is that you really cast a very bright light on the frontiers of the research domains that you're interested in. It's okay if there's controversy. It's okay if you're going to say something that you know other panelists might not agree with, and we would love that discussion. It's an opportunity for you to send your message to people that are not in your group, but that are going to be the next generation, and that's the way that you can leave your mark in the field too. Share your wisdom about how to think critically. This morning, we had a lot of thoughts about things that used to be conventional wisdom and that turned out to be wrong. So that's great. These things like these are always good to hear for the young generations. Always, let's keep the message of basic electrochemistry. Remember that this is a program on electrochemistry. That's our most important goal. For those of you in the Zoom call, get involved. Mute your mics until you're called to get involved in the discussion. The way that we're going to do this, it's like this morning, worked really well. Post in the chat of Zoom that you have a question, and we are taking notes on who is in the queue for asking questions. We'll call you to the floor, and preferably you ask yourselves. If you have an issue, mics, cameras, anything, let me know when you post the question, and we can always read it for you if you want. Don't be afraid of challenging the faculty, and think broadly. Think beyond this program, think beyond what you've heard. Try to connect things between panels, and think beyond what you're going to do in your PhD or in your postdoctoral studies. With that, I am going to stop, and we agreed before we started on an order, and we agreed that JiaBin Huang was going to be the first one. JiaBin Huang joined us from the University of California, Irvine. Just like Irina this morning. So Jenny, whenever you're ready, the floor is yours.
Okay, thank you so much, Jordi, for organizing this and for inviting me. So excited to be on this panel today. The first thing I want to point out, which is a sort of a quick plug, as Jordi mentioned, Irina also came from UC Irvine that spoke this morning. And so this is a mock-up of a new building that's almost complete on our campus. And we have been trying very hard over the last few years to build up our electrochemistry program with many different researchers, and many of us will be centered in this building. So Irene and I are both moving in and hopefully be neighbors so that we can learn more from each other, as well as several other electrochemists within the engineering and the physical sciences schools. Okay, so you got a good picture of this morning about thinking about the future, and if we are moving to renewables, it really means electrification, and that means, thinking about trying to use electrochemistry to do many of the processes that we currently think about doing thermally. And there are many different ways we can do this, with heterogeneous or homogeneous catalysis. I'm a homogeneous catalysis person, and then you can also think about different ways of photoelectrocatalysis, so photoassisted electrochemical type transformations. But the different things that we can think about doing that we currently do thermally are, of course, N2O2 ammonia, which was mentioned this morning, generation of carbon neutral fuels by recycling CO2 into liquid fuels. And then, if we think about moving away from fossil fuels are currently, a huge feedstock source for materials and chemicals, right? So we basically, in order to reduce or to get better atom economy in the fossil fuel industry, so many different industries have learned how to use sort of the unneeded products, ethylenes and things like that, in order to generate everything that we make today. And so we want to find ways of replacing those feedstock sources as well. So I think there are a lot of opportunities here. One thing that I didn't see mentioned this morning, but I think is interesting, is that, all of our chemistry using thermal reactions, we always think about the product distribution being a thermal distribution, because we have to, right? Because they're done at high temperatures, so we can't avoid a thermal distribution of products. But I think if we go to electrochemical conditions, which are ambient conditions, and we think about low temperature distributions as well, or access to different products that we wouldn't be able to get to otherwise. Obviously, lower infrastructure requirements, and then the distributed argument is interesting, as Marta pointed out this morning, about the different resources, but you can sort of consider that most places have renewable resources. Of course, the cost of electricity is different, but every place has, all the component feedstocks that we want to use: water, CO2, N2O2. Okay, so when it comes to catalysis, a couple of things that I wanted to bring up that I think are general is that when people started getting very interested in electrocatalysis a little over a decade ago, as renewable electricity got cheaper, I think one of the really valuable tools that we used in the beginning is calculating volcano curves. And I think it was very valuable to help identify sort of important intermediates, bond energies, and for catalyst discovery. But I think we, in some ways, need to move past a lot of those simple models and make them more complicated now in order to get a better way of doing catalyst discovery. And so we need to account for different mechanisms for complex reactions, which is not straightforward. And part of that is we don't know all those different mechanisms, which is why we sort of need the second part of the experiment so that we can learn what mechanisms are possible. And then how do we use secondary interactions or local environment, right? So this is becoming much more popular to think about interfaces as a way to modify those intermediate energies and maybe move off what you would normally consider those volcano curves. And also, how do electric fields and varying potentials influence those different calculations? And I think those things were sort of, the simple model, maybe not explored as thoroughly, but now as we become more advanced, we need to think about those different things. And we need the methods, of course, experimental methods, to help feed into those theoretical models so we can use them predictively. Another one that I've actually been working on for a while is general to reductive catalysis that uses protons, and it's basically getting rid of parasitic hydrogen generation. So this is important in organic electrosynthesis as well as chemical fuel generation. And so, we've been working in our group for a long time about how do we suppress this reaction. Although it was an interesting point I think Dan brought up this morning, is that now that joules are cheap, do we really need to worry about that as much? I mean, what is it? What level is acceptable as electrons become cheaper? And then I work in the broad area of artificial photosynthesis and trying to understand these reactions. And so I think some of the important questions are, if we do CO2 reduction to fuels, what should we make? And we don't do these type of analyses, but I know other people publish them, and it's worth looking at to think about what are the best products to make in terms of economics right now, and where can we have the most impact, and whether or not we need to make fuels directly, or can we make feedstocks that can be upgraded through traditional thermal methods fairly efficiently. On the anodic side, I think a student brought up this morning, which is a great question. I think it was Joy who said, is there better reaction for the anodic side, and I think there should be. So of course, we model artificial photosynthesis after plants, which of course do water to O2, but O2 is not valuable to us. Can we replace it with something at scale that will generate something useful, biomass oxidation, or something where we can actually, basically make money off both sides of this electrolysis? And then also for both sides, can we use dirty feedstocks, right? Because resources, clean water, clean CO2 are not always available, and so what tolerance do we have for that? I think that's important. Those are important questions. And I added something briefly because it's something that I've become very passionate about, and it was brought up this morning, which I think is important, is electrochemical separations as well. So we started working on electrochemical CO2 separation last year, because one of the things we realized with our CO2 reduction work is, of course, we always use a pure stream of CO2 we buy, clean CO2. And if you look at the numbers for CO2 capture, they're so bad that we can improve our catalyst by several hundred millivolts of overpotential, but it doesn't really matter because most of the energy is going into purifying the CO2. And so how do we fix that? And so, electrochemical methods have the potential to be much better than current thermal methods. And I also think that, these can be applied for other things like F elements, critical materials, recycling. And so there are a lot of other issues as well. And I just wanted to point that out because I'm happy to chat about that as well.
Okay. I am going to apologize because I have the double audio. I'm trying to figure out what I'm playing in the background that I'm hearing. I'm still hearing JiaBin. So we're going to move on to the next person, who's Aleksandra Vojvodic. You probably hear the double audio too, from University of Pennsylvania, and I'm going to mute myself so that you don't hear it anymore. Thank you. Whenever you want.
You're muted, Alex.
Yep, I had multiple screens on. Let's try this again. Okay, here we go. Can you hear me? And do you see the screen? Okay, awesome. So thank you, Jordi, for the invitation to participate in this panel. And I really much look forward to this discussion and to interact with the students. Before I start, I just want to relay a thank you on behalf of my students who've participated in these events in the past. They loved it and they find it extremely useful. So I hope this event continues in the future as well, in person, hopefully. So let's see here. So this specific panel is supposed to be on electrocatalysis. Just as Jenny pointed out, we should always take a step back and try to consider things in the bigger scopes. So my frontiers can all basically go under the umbrella of photoelectrochemistry and physics, because obviously these are multidisciplinary questions that we have to target and deal with, that have to have input from chemists, physicists, material scientists, et cetera, which I hope you're able to see from the panel compositions here as well. We've heard a lot about thermal catalysis this morning, how it differs from the electrocatalysis, the benefits and some of the not good things about it as well, that it works for some chemistries and not for others, and some of the fundamental limitations, right? So what I wanted to do is basically then focus the discussion, so specifically on electrocatalysis. Okay, so there are a lot of applications where we see electrochemistry taking place, so electrocatalysis being one of them. Obviously, batteries are another example where there are electrocatalytic reactions that are taking place as well. There are fuel cells and many others as well. So a lot of researchers would put themselves in the application bucket, but of course, a number would also put themselves as fundamentalists, meaning that they really want to focus on the phenomena and the fundamental science that is taking place in these applications. So my group focuses on both because I do believe that you actually need both to figure out how they're connected, not only for a specific system, but between different applications and between the application as well as the fundamental science. So what I do think is the key question to target for us is basically the following. how can we obtain, harvest, and tailor interfacial phenomena at different length and time scales? So this would encompass basically, how do we think beyond just the single material that we want to design for a specific chemistry, but really try to combine materials, right? If we want to look at an electrocatalytic system or a battery or any other system, in the end, you need to combine systems. You need to combine materials, or you combine, inorganic solid material with the soft or squishy polymer, an electrolyte, or whatever you might want to have. You're creating an interface between these two. And that's really where the chemistry catalysis is happening. That's where you really ultimately want to target to focus your applied potentials, your fields, and you want to really understand what is happening at that interface. So how do we obtain that information is crucial. It's been a long-standing problem, I believe, in all of these areas of electrocatalysis, as well as in electrochemistry in general. It's really hard. Computational researchers have been able and are currently working on a lot of this, as well as a lot of experimental tools that are being brought on board. So not only do we need to obtain the information, but we also need to learn how to actually control it, kind of. So that's the tailoring aspect. So we need to do this not only at the angstrom scale, the smallest scale, but also at the nanometer scale and the micrometer scale. And all of this, we obviously have to do somehow while it is happening, while we have applied the potential where there is a liquid water or an electrolyte present. So it's like big challenges, basically. And I believe that for us to do this, again, we need to collaborate. We need to really unify. So this is just showing you a schematic that, yes, we need both theory, computation, and experiment. I think a lot of the groups out there are kind of jumping on board on this and can stand behind that. So this is not that controversial, but I think we need to do more of that and really compare apples to apples, and not, let's say computational scientists calculating specific theoretically defined numbers and then comparing it to experimentally measurable numbers. And they obviously don't match because they're not really measuring the same thing, actually. Jenny pointed out volcano plots, for example. They typically only measure either thermodynamics or maybe part of the kinetics. They don't take transport into account. They don't take into account the fact that we have charges moving around, et cetera, et cetera. Right? There are like a lot of things that we can add to this. And the other thing that I think we need to do in the sense of borrowing information and borrowing techniques and knowledge from the different fields. So some of us grew up learning the language of one of these subfields, but we should really talk to each other to learn. We could also look to nature and see what exists out there, something that nature itself has developed over many millions of years. Why is it working? And why can't we artificially reproduce some of it? And why isn't nature able to reproduce some of the other things? We've heard about Haber-Bosch. Obviously, nature does that as well. It produces ammonia at ambient conditions, but it does it much more slowly. So it's like totally different conditions. How can we learn from these very different things? So for us to really design things, we'll need the understanding. And also we need to learn how to use what we have on this planet, right? So really use earth abundant compartments, basically, right? So earth abundant metals, for example, not only for the materials that are used as catalysts, but also, converting CO2 because we have a lot of it. So with that, I hope to open up for questions, or hand it over to Feng, probably is the correct thing to do. Okay, great. A quick note. So I was complaining before about double audio. If you hear that happened to a person earlier, so I'm gonna make an announcement before I go to Feng, just real quick. The YouTube, if you have the YouTube live cast open, it automatically plays, and so that you'll start hearing things twice. If that happened, make sure that you have all your browsers and everything closed, so that you close the YouTube. That's what happened to me. I had a browser that I didn't even know I had open. So imagine that. So with that, there's always some hiccups. I'm going to go to the third panelist who's going to be sharing his thoughts. This is Fang Zhao from the University of Delaware. Fang, the floor is yours.
Thank you. So let me. So good afternoon, everyone. and it's my pleasure to share a little bit my thoughts on the frontiers in electrocatalysis, particularly. So first, I give you probably just a 1 minute kind of short summary of what I do in the past about a decade at the University of Delaware. So I'm trained as a chemist. Then I'm working in the chemical engineering department. So I saw some of the key differences between fundamental research versus more applied kind of research. Actually, electrochemistry brings these two pieces nicely together. We work on a lot of catalyst development, as Jenny in the very beginning mentioned, how to rationally design catalysts. This is definitely a very important topic. And also we're working on some operando techniques, really trying to understand what's going on at the electrochemical interface. Go beyond that, another very important, particularly for engineering, from an engineering perspective, is how we actually can design a very effective electrochemical reactor, which can effectively execute the reaction you want to do, and in a very efficient way. And of course, an efficient way involves you have to achieve a high selectivity, high energetic efficiency, and also probably a long durability. This is sort of the things that we actually got involved in last decade. The only one piece actually I also list on this slide is the so-called tech economic analysis. Because nowadays, as other panelists also mentioned, the cheap electricity become a more abundantly available to us. So people start to think about, is there any commercial opportunities? So we actually dig into this kind of economic aspect of electrochemical systems and looking into what's the key gaps actually prevent a certain technology to enter the market, or is there already opportunity for certain products could be commercialized or process can be commercialized. This actually gives us a lot of guidance in terms of how we can design more efficient systems for practical applications. So what I think from particularly in an engineering perspective, the frontiers in electrocatalysis. So first thing I want to say is electrocatalysis is not just about the electrocatalyst, okay? This is way beyond just electrocatalyst. When you put an electrocatalyst into an electrochemical device, the catalyst actually sitting in a very different environment. Okay, this is the key difference I see over the years is when we start thinking about how to rationally design a catalyst, but because the tools we have at the moment is actually limit our capability to precisely replicate the realistic kind of environment when the catalyst is actually under working condition. For example, this is one of the schematic I use to just give you sort of ideas what's going on if we do, say, CO reduction or CO2 reduction, similar situation using copper catalyst. First of all, you have to realize I put a kind of spherical particles there, but actually catalyst is never become a ideal kind of spherical particle. It could be nanostructure, could be have a certain shape, can be even have different shapes of exposed different facets. And then you put on the kind of support, a common support we usually use, a common support. So you're actually dealing with those catalyst support interactions. And then I use this orange-ish, yellow orange-ish color to represent the anomaly we put on the catalyst. Anomaly put on the catalyst actually to enhance the ion transport, okay? This is the set of things we commonly do in an electrochemical device. And these kind of anomaly interaction with the catalyst also could influence the behavior of your catalyst. Of course, if you're really talking about reactor, you have to deal with those mass transport issues. Could be reactant product rated, and also ion and electron distribution is critical to achieve an efficient electrochemical device. So this is sort of I think we really want, but I don't really have an answer yet, is how to rationally design such a kind of a system. What's really the design principle beyond just the electrocatalyst itself? And what kind of tools allow us to prove and understand the system, particularly the interface? And also, I will say research is more curiosity driven, in my opinion, at least. Is there any new reaction, new chemistry we can do with electrochemical tools? Working in the electrochemical domain for a couple of years, I realized people always talking about 4 reactions. OER, OR, HER, HOR. Now CO2 kind of the 5th reaction. So we stuck with these 5, but we can go beyond that. Okay, this is kind of a personal opinion. And I'm looking forward to interaction with all of you, and maybe we can inspire each other and generate some new ideas. That's all I want to share.
Okay, thank you, Fang. Great. So that completes the opening statements, and we already have a question. So I am going to go straight and open the floor to Arti, who has a question for you.
Hello, thanks a lot for the opening remarks. They were really great in trying to link up everything from the basics up to the application scale. And that is what my question is also. So how significant is the role of ions at the interface? Like I've been doing, I'm an experimental postdoctoral researcher, and I see that there is an influence of having certain ions at the interface in terms of what currents we can get. However, do they really make a huge change in the output at scale, like when we try to put them in a reactor? Does that really matter to a huge extent or not? Because I am not able to see that right away. So that's what I came up with.
All right. Who wants to take that on?
Okay, I can jump in, start to respond. So yes, what you mentioned is definitely an interesting phenomenon. Let me use just a CO2 reduction as an example, which is one of the reactions I'm very familiar with. There are a very recent report on if you add some potassium at the interface, particularly concentrated potassium, actually can accelerate this kind of a system, particularly improve the efficiency and the selectivity. Almost complete suppress hydrogen evolution, which is amazing. So right now, there's, at least my understanding, there's no comprehensive understanding what's exactly going on. But my personal belief is this is definitely a very interesting topic to understand how those cations or even anions near surface of the catalyst influence the catalyst behavior. This is definitely a topic very relevant to reactor engineering, because at the realistic systems, depends on how you design it, I have to say, you may completely get rid of those supporting electrolyte. It's possible. For example, CO2 systems, it's possible you can just run just DI water without any salt in it, just using membrane as an electrolyte. But in other systems, if you have a concentrated salt, you already demonstrate this, actually can enhance the performance significantly.
I'm going to use this question to broaden that point a little further, because I can see where Art is coming from, and I'm taking notes on the things that you're saying, and you've all made reference to things that happen at multiple scales. There was this concept of designing the electrocatalyst beyond the catalyst, the electrocatalysis beyond the catalyst itself. And so then I wrote right next to it, this just feels very daunting. Where do you even start? How do you even go about doing this? Are we scaring the next generation into, it's hopeless. Any ideas there? Where, how do you go about starting somewhere?
Yeah, I mean, if I may add something that people have in the past, obviously faced similar type of daunting challenges, right? So if we go back to the prototypical Haber-Bosch reaction, where nobody knew anything, we just knew that we needed ammonia. Scientists and engineers went out and actually were digging out different materials that they tried. There were like thousands of materials that they actually tested and tried. So I think that there is a part of it that will inevitably be, we need to try different things. But I also think that there's the understanding, like, why isn't something working and why is something working, right? So it happened to be the case that, the Haber-Bosch process, it found its ultimate material in terms of its performance and the cost being an iron oxide ore, which had potassium atoms in it, right? So that is, it all came in one system and it was available there in nature and the individuals found it, right? But so I think the question is that I believe that there are two answers to this question. One is we need to do the brutal force. You cannot not do that because there's an exploration phase, but then we also need to dive deeply and study very well characterized systems to understand. And it took many years before it was understood that potassium does what it does to the ammonia synthesis process. So I think, as Arti and Feng pointed out, different ions will do different things to different reactions. In some cases, they will be promoting stuff. In some cases, they will be parasitic, they will be passivating. So I don't think that it's a single answer to all reactions and all questions. So I think stuff can do different things to interfaces. And that's the cool thing, that there's so many different parameters, but obviously it's daunting to map it all out. You don't need to start from scratch. There's a lot of stuff that has already been done by the scientists and the different communities, right? The surface science community has been studying, how do you add promoters and ions in a way as well. So we can reuse things. I think key is not to reinvent the wheel, but map out what is already there and then fill in the gaps. That's at least my thought on it. And then computationally, obviously, obviously we have very, very well defined. We think if we know how to model it is the big question, obviously. Sorry, go ahead, Jenny.
Oh, it's okay. I totally agree with what you and Feng said. And I just think that trying to design experiments that can interrogate that. So I also found that study pretty interesting. And I do mostly homogeneous catalysis, but we always usually see the electrolyte as sort of innocuous, and it's just something there so that we get conductivity in solution. And we don't really think about the identity. And I think some of the things that I've seen recently in some of the heterogeneous literature is sort of exploring, the effect of, so the Lewis acidic cations have been shown to be promoters. And so the question is it because they're cationic, or is it because they're Lewis acid? And it's a cationic in size. And so you can look at, ammonium versus triethyl ammonium, tributyl ammonium, just different sizes of cations to get sort of to try to parse out, how much of it is a charged localization effect, how much of it is a Lewis acidity effect. You can use other Lewis acid additives that are neutral, like boronates and things like that, if you want to isolate those effects. So they're different. I'm a chemist, so we always try to find these chemical solutions. We can isolate these effects and try to understand, once we observe the phenomenon, what exactly is causing these effects that are promotive.
One other one that I wrote down that struck me, because I don't have a lot of experience in this field. So it was this concept of going beyond the volcano plot that you brought up, Jenny. This strikes me as, we are telling chemistry students that what we told them as undergrads no longer matters. Sabatier principle goes out the window. What's your perspective on this? What happened? What broke?
I think Alex is great. So Alex and I have talked about this quite a bit, and this is how we met actually a couple of years ago. We got into this at a meeting, and in a polite way, of course. And that's why I've enjoyed talking to her so much, because as a computational chemist, because I think, in the beginning, as a simple first pass, it was great. But then once people started really getting into it, it was much more complex. And I don't understand all the variables about it. And I think Alex has been great actually at also sort of digging out, what needs to be, how do we take it to, the next generation and the generation after that, in order basically to keep improving our models, because at this point it's not quite predictive in the way that we would like it to be, but I think it can be if we work on that. So I'll let Alex talk more about that.
Thanks, Jenny, for always, I always have awesome discussions with you. So thanks for continuing that. What I'll add is, science is all about models. So volcano plots are model. The Sabatier principle, right, came, and we didn't know what a descriptor was. We didn't know what to put on the axis of a Sabatier principle. So we know today that we can, at least find ballparks, I believe, by using these volcano plots, and especially map out, as I pointed out in my slides, some of the thermodynamics Some individuals have also targeted some of the kinetics. But in the end, especially computationally, if we take this approach, it's all about mapping out all the reactions. If we don't map all of the possible reactions, we will not be able to get the right volcano plot. In the same way as if you use a microkinetic model, it will only give you what you put into it, right? So this is kind of what's the drawback. So how can we automate things, and how can we really map out phase spaces? And this is a general, as a computational scientist, I would say, how can you ensure that you have found your maxima or minima? And that is not always trivial, because it's a many-body problem that you're dealing with in most cases, right? So it's not a simple solution. I think we can include more and more layers to the different models, and the volcano plots can evolve, basically. I think the key thing, which is going to be hard to include in a volcano plot, is really the evolution of the system, right? So at that interface, if it's electrified, if you have some ions, or if you have added an electric field, or some bias of some kind, you're perturbing your system in one way or the other. How do you take into account that you have the right phase changes of the material at that interface, et cetera, et cetera? The restructuring that somebody brought up here earlier as well. So it's like, those things we can't do high throughput computationally currently. That has to be done on a specific system or a few systems. And I think that is something that the computational science needs to work on. But I think that, the volcano plots have their spot in the same way as Newton has its spot, despite Einstein, I would say.
Okay, that's,
right?
That's a very good way of putting it.
It's simplified, right? But it gives us a grasp. We can understand certain things. We understand, for example, why HER is dominating over NRR. We can get that from basic things, even thermodynamic. We don't even need to think about kinetics at all, right? But that doesn't tell us, how do we go beyond? How can we solve the problem? So I would say that's the biggest limitations of the plots, that they don't tell you, what do we do to solve the issues? They can identify and describe some of the things. Mm-hmm. And then they can find some materials that potentially could be the starting point for some of these evolution or dynamic type of simulations or experiments that we want to do.
If I connect this to what Fang was saying before I go, so we have some questions popping up. Would the volcano plot ultimately then end up being dependent on how you're measuring your catalyst? So you could take the same catalyst and put it in different conditions, in a different support or in a different set of electrolytes. And the problem is that the volcano plot then changes. Is that the issue?
I mean, in the same way as, so a volcano plot, again, it's giving you a turnover frequency ultimately, or an overpotential, a theoretical overpotential that obviously changes depending on what system that you're studying. So if you study supported metal catalysts versus unsupported, the answer of the top and bottom is different. So depending, like we've seen a lot of these volcanoes that are basically, they're cuts through multidimensional space, and we probe specific parameters in that multidimensional space. So working conditions, as Feng pointed out, for example, they're parameters, but we haven't probed them. We haven't explicitly modeled them always. So if we do that, I think we can have, highly dimensional functions, which are what the turnover frequency, a multi-scale model really is. That's at least my take on it. So I'm all for generalization, as you can hear.
That's what I was getting at, right? There's still rules that you can get out of this. Any other thoughts before I move on to another question? Okay, Aditya, you said you fixed your mic. Do you want to pose your question directly to the panelists?
Sure, yeah. I hope everyone can hear me.
Yes.
So yeah, awesome. So, well, my question to the panelist is, as somebody, I'm doing my PhD right now towards finishing things up, and I have been recently getting into probing the electrolyte surface with some in situ techniques like ATR, IR techniques and all that. So my question here is that some of these techniques, the surface probing techniques, that give us insights into the reaction mechanism, but they are sort of like limited because we are working in some sort of different hydrodynamic environment. Like if somebody's using like a gas diffusion electrode in an actual cell, you cannot do that in certain in situ techniques. So I would like to know your views on what do you think about how could one be working around such difficulties, or how could this affect our understanding of an electrocatalytic reaction?
Who wants to take it on? It's the eternal model system question.
Okay, I can jump in again.
All right.
I happen to work on infrared and the electrochemical system for a couple of years. Actually, mostly through collaboration with my colleague, Bingjun Xu here. So my kind of thoughts on this type of technique is, I think the major challenge is not saying this, probably there's a big difference between a realistic system like a flow system versus a user and gas diffusion layer versus ATR cell. I think the biggest challenge right now, I think this type of technique facing is they don't have any time resolution. Basically what I'm talking about is you can't see any intermediates. Most of the intermediates just not visible in infrared or even surface enhanced Raman, those kind of technique. That I see is when we're looking at infrared, looking at the Raman, and doesn't matter if you use a silver, gold, or copper, different catalyst, the things you can see is mostly CO probably, if you do correctly. And those very interesting intermediates like C2 intermediates, no one really see it. So that's kind of I see as the biggest challenge. I hope the next generation electrochemistry can try to dig into it, really develop this, push this, the edge of this technology. And I think there will be a breakthrough in that end.
What do you think about the topic of translation? Because that's another aspect of what Aditya was talking about. You know, how do you translate what you're doing in a system where you've had to reduce your complexity so that you can do the measurement all the way back? This kind of applies also to the models, right?
Yes.
You know, we're talking about how the models are.
So but that's also a good question. So at the very beginning, why we're doing it is trying to understand very fundamental question is how the two electron reduction occur on the surface of a gold. Very simple catalyst, very simple reaction. We started from there. And then we realized, even with that two electrons, there's a lot of debate on it's a single electron transport first or proton coupled electron transport. You know, there's a lot of debate in the field, which actually infrared actually helpful in that sense, provide some of the information. At least you can sort of probe with different pH interface. At the interface, you can sort of get some sense of whether the proton is directly involved or carbonate is directly involved, this kind of information. But if you want to go beyond, be more powerful, then you need a time resolution come in.
Okay. I'm going to read a question.
Sorry to interrupt you. I just wanted to add one thing. So
sure.
Very often, and I'm not an experimentalist, but the rest of you correct me, but there is one question of, you know, observing the intermediates and seeing the products. And there's also the other one, seeing what's happening at the interfaces and the changes of the material. So there are multiple different things that you can measure. And obviously there are new techniques that are coming on board where you can do operando. We can even look at the solid liquid interface and the explicit changes at the atomic level, right? There are STM operando studies, there are AFM operando studies, there are high resolution TEM, and obviously we have all the X-ray stuff at the national labs. I just wanted to bring that up so that it's out there since we haven't brought it up earlier.
Sounds good.
Oh, I forgot to mention one thing, sorry, I have to add this, is I think one of the challenge, also the other kind of a key challenge I see as infrared or Raman to study electrochemical system is if you see some species there, then that means those species actually is intact with the active site because the heterogeneous nature of the electrocatalyst. this is, oftentimes people just completely ignore it and pretend this is just active site. You are looking at active species, but maybe you're not. So we never sure, 100% sure, we're actually looking at the active site, the species absorbed on that active site. So I just want to add that.
Is that where coupling with models may help you? Because you could at least, probe the hypothesis. If you see that floating around, you could say, well, under what model would this thing become part of the active site? Right?
Definitely, I think modeling is definitely helpful. Just from experimental side is most active site, the surface coverage may be very low. So which means naturally you can't see it.
Right. Yeah.
They don't stay very long. If they stay very long, become poison, right? This is kind of the challenge.
I'm going to read a question from Saket, who has an issue with his microphone. Yeah. So it takes us back to the question of the influence of cations in the solution. He says, we have also been exploring the cation effects in detail. And one thing that we found interesting was that the cation effect is very strongly dependent on concentration. And the traditionally invoked mechanisms, for example, Fromking effect, are no longer applicable. What are the panel's thoughts on combining experimental and computational approaches to study these effects?
We're sort of just early studying sort of cationic effects, but I'll point out that one of the things that I think is pretty interesting is some of the work that Johan Dalati at USC is doing, where he attaches probes onto electrodes and then looks at local electric field as the dependence on cation identity and concentration. And I think that's sort of an important aspect of looking to see how it changes the interface when you apply a field.
Isn't part of this also that this is a very new idea? The idea that, what salt you put in your electrolyte, Feng presented the concept of beyond the catalyst side, but that's generally something that has come out in the past few years. This wasn't necessarily long-standing tradition, right? Am I seeing this correctly? So that's then part of the answer is that, this is a very new, so it seems, Saket, that you are going to be one that's going to clarify some of these things based on what you're observing.
And then adding to that there's, we think of these ions, but there's also, there might be other things in your electrolyte, which I think have popped up, that we heard about cleaning your streams of the reactants, but also cleaning the electrolyte. So depending on how dirty or clean your electrolyte is, might also present some challenges at what you're actually measuring and what is participating in the reaction and what the coverages are, et cetera, et cetera. So there are ions of other types than the ones that you are maybe thinking that you're having, depending on how you prepared your system. So that's the other big thing I think that the community is kind of learning to make sure to control for what's actually in the system.
I think the other interesting aspect for reductive catalysis is proton source too. Certainly in organic electrochemistry, which I do, that seems to matter, right? And not beyond just the pKa, but like buffer identity and things like that. And so I think that's sort of an interesting question that I don't think is completely resolved yet either. So sorry, I don't have any more answers, but I know that these are areas that I think are sort of active at this time and unanswered.
So these would be basically whatever you add as the counter anion for your buffer can actually have an influence as well.
Yeah, the buffer identity itself, right? So there was actually, I see Prashant on the call, there was an ACS Energy Letters, it was a homogeneous system, but they were noticing differences in HER activity based on buffer identity, even at the same pH, right, formal pH. And so clearly that can matter sometimes, in terms of proton transfer. And that's something that I intuitively would not have expected. To me, it's just proton activity, but clearly there's sometimes where it comes from can play a role in salvation, things like that.
Yeah, you're touching upon a topic now, and I'm gonna just add this note, and then I'm gonna move on to the next question of the role of salvation, which is one of those things that is kind of overlooked classically. And we have a panel in the after, our last panel of the day is actually on that, because it turned out that, it's important not even for not just for catalysis, but it turned out that it has a major role in energy storage in batteries as well. And that's also another effect that seems to me like it's a very new thing that we're discovering, right? That, the solvation shell does its own things as well. I'm going to move to the next question because we've been accumulating them. So Jessica, you had a question. Go ahead, take the floor and ask it.
Hi everyone, my name is Jessica Ortiz Rodriguez. I'm a graduate PhD candidate at UC Davis. And my question is along the lines of the electrochemically active surface area when we are reporting hydrogen evolution, CO2 reduction. I see some smiles, but usually we do this in the community. Well, geometric surface area, we're trying to move from there, and there's some papers actually now that to submit, you have to report the electrochemically active surface area. However, for that, you need the specific capacitance, which might be a problem to get. So I have seen some papers just reporting double layer capacitance. As some papers have shown, if you have a porous surface, that can also add capacitance that is not coming from your catalyst, but just coming from the surface itself. So I have also seen papers that they use sulfurous probing to identify those sites and normalize it that way. However, that I don't consider that will be that will be feasible if we're running a lot of experiments. So during with this challenge, do you have any comments of the most appropriate way to report figures of merits of current density in a way that we're accounting for the real area and not just the geometric or having the problems associated with the double layer capacitance?
Okay, let me try. It's a very interesting topic, I have to admit. There's a lot of discussion, I think, in recent years about what you should report. So my personal opinion on this is it really depends on you are working on fundamental research or you are more towards the applied side. Of course, geometric surface area matters in applied side. And for fundamental research, definitely, I think to estimate the accurate electrochemical surface area actually is very helpful, because then which allows you to calculate tone frequency, understand the activity of your catalyst. So in terms of how to measure it, I don't think the community have any concerns on what is the perfect method. Okay, what do you measure in like a double capacitance measurement? We use a lot. Or under potential deposition, right? For certain metals, you can use that as well. And even just like you said, just measure the size and calculate it. That could be another way to do it. I'll even see papers talking about using BET surface area to represent the surface area. So I would say it's hard. It's hard to really measure it accurately. To be honest, I would say most of the time, double capacitance give you a rough estimate close to the number. To be honest, I don't know which one could be more universal for all the metals you have to deal with. So the metals is actually much tougher than others, like copper. As I know, there are not many methods actually you can use to measure the surface area very accurately. So I let the other panelists to comment on this.
I mean, this is kind of a perennial, debate, right?
I think it's a really good question. I think you should ask it during the publishing panel, because I don't think there's an easy answer. And even just electroactive, I think it's good that publications are now putting out standards of what they expect to see, so that at least you can get apples to apples, even if they're maybe not the most accurate representation, right? But at least you can compare something that with something else. It's a little bit, allows a little bit more information.
And I will take that opportunity with what Jenny just said to repeat something that I put on the chat. It is totally okay to ask the same question in multiple panels, because you'll get different answers. I can tell you from experience from last year. So There was one person last year that asked exactly the same question in every single panel, and he got different answers every single time. Related, none of them contradictory, but different angles. Okay, so definitely do that if you want. Alex, did you want to say something?
Well, I just wanted to add to this. I mean, you've seen a lot of papers, or more and more papers, where scientists compare experiments and computation and theory. And in that case, it is actually very, very hard. I mean, you're not always comparing the same things. So I would say the key thing, independently of what metric that you're using to measure the experimental numbers, or normalizing them with, is to, if you have a trend, if you have a few systems, you compare across those. You hope, assuming that the mechanism is the same, assuming that it's similar active site, as there are many assumptions, right? But just because you have, a match between three numbers that somebody has calculated on 3 random systems, and that those seem to be agreeing with the trend you're seeing on the 3 different systems that you measure, does not mean that you have understood or understand the origin or the phenomena for that matter. So there's a bigger issue, I think, both experimentally, but also when individuals are trying to use computation and theory and models to explain what they're observing. So what are we trying then to explain if we don't agree what we're actually measuring? And then what are we modeling of what we don't agree that we are measuring? So there's like multiple layers, I think, to really comparing, as we've said a couple of times, apples to apples.
From your experience, though, how do you go about navigating these treacherous waters? What is the I mean, for the 3 of you, again, this can feel, and this is classical for electrocatalysis or catalysis in general, is that it's many parameters and it can feel like you're trying to optimize many things at the same time, right? It's like you're on a boat and you have all these holes in the boat and you're trying to cover all the holes and you don't have enough fingers. How do you go about navigating this yourselves, from your experience, when you have this issue of being able to benchmark? Are there publications out there that you would recommend that the students take a look at, or methods papers, which seem to be more popular these days? Anything that you would want to share in terms of where to start?
I will usually suggest my student to do a comparison just by ourselves. So this is the best way to do it, at least my opinion. Of course, this become a time consuming if you're talking about, say, 10 different catalysts, right? And some of the catalysts are synthesized using very unique way, whether you can, 100% reproduce the same catalyst, that's also questionable. May take some time to get there. But if this is really critical for our research, definitely I would suggest my student to do by herself, rather than just code a random paper, say, hey, they reported this value, we just take it. Because then if you do comparison, this become a even bigger problem, because everyone using slightly different loading, slightly different method to fabricate the electrode, slightly different method to even measure the surface area, right? Just like what we discussed. And how you make sure your comparison is a fair comparison, right? It's likely your paper get to one of them's hand and they review it and say, hey, you treated my data wrong. This is common complaints you may see when you're trying to publish a paper. So that's why I feel more comfortable if my student do all the catalysts using our method. It's kind of standard procedure, and then we compare them. I will feel more comfortable in that way.
Yeah, but I mean, computationally, there are many aspects from, which computational model do you choose? That's a theory. And then there's what model do you actually use to model the specific, the catalyst that Feng made. And even if he or anybody else in the community uses the same recipe, it might still not become the same beautiful nanoparticle that does exactly that thing that somebody suggested, right? So there's like many layers. But what we have found is, always do multiple levels of theory is one thing. Try to benchmark with very, very detailed surface science experiments so that that you at least, you get the electronic structure right. If it's a semiconductor, make sure that your method can model and capture that in your system. And then compare to, very detailed atomic level data that is available. So we very often collaborate with people that are doing STM, AFM, high resolution TEM. And then you have to manage that bridge between that model system and the actual system. So just, I mean, there are very few studies that where you actually can really follow the system from that small scale when you have the solid liquid interface. And then you say, okay, these peaks in your IV curve correspond to this exact coverage of this exact intermediate. That does not really exist, actually. There are a few attempts. I mean, there's a few series of beautiful papers on platinum and ORR where individuals have studied it. And that's really beautiful, but that can, I mean, it's so time consuming. It's decades of work. So it's not maybe feasible for everything. So the question is, what is reproducible in a feasible time frame? So again, coming back to one of the questions that we had before, how do we navigate this massive parameter space? And I don't think that there's a single answer to that particular thing, but just comment on the computational side. And also, you know, there are a lot of different databases. So it is more or less customs today to upload. Once your data is published, you upload your data into one of these. There's so many. Don't attempt to make, I would say, don't attempt to make a new database. Try to connect them or add to the existing ones, and then consolidate the data and get information from there. Because I know there was one question asking about how do you go about, there's so much information out there in publications.
Yeah, Wessel had that question. He mentioned that we've already covered some of the things that he had in mind. Wessel, do you want to add anything?
Yeah, I can change a little bit. From my experience in the battery field and everything, a lot of people report different metrics and everything, especially in the case of nanomaterials, where they'll kind of sell you the moon, where, you know, it's so stable, it's got all this, you know, great capacity and everything. And then when you look at their experimental, it's, you know, they load it with carbon, they have a ton of electrolyte, they have all these things that aren't quite realistic. What are the common pitfalls that you see in, you know, the space of electrocatalysis that, you know, people should generally avoid to give like honest reporting?
I love this question.
Okay,
who wants to start?
Oh, let me start. I love this question. So I guess you working in battery long enough, you probably know the famous story about the lithium sulfur battery. Started with extremely low loading, and people reported it's extremely stable. Okay, that's one of the tricks I learned. Then, you know, if you look at the electrocatalysis, exactly similar kind of things you may see. People report that catalyst is super stable, but if you look at the current over potential, extremely low over potential, extremely low current, they claim it's lasted like forever. But come on, really, you use catalyst as that kind of condition? You never, right? Just like a battery system, you never load your active material like a 0.1 milligram per square centimeter. Are you kidding me? So, okay, I just throw out this, you know, statement here. So I let the others to me. So.
If I may add to this, I love the superlatives you picked, Feng. I think that's been a big trend over the last X number of years in any of the fields that we've mentioned here, is to have beautiful adjectives to describe one's system. And every time you just have to have a higher number, have a higher performance in whatever the metric is, which, I mean, is not obviously feasible, because in the end you'll hit the limit of making, you know, a perpetual mobile, basically, right? Which is not feasible. So by understanding why and what component that is contributing to what you want to achieve, I think is what you need to target. And I'd say that, I don't know if there are any individuals from the publishing offices, it's not always clear that is being awarded over the high numbers or high metrics. And that's, I think, something that has to change. And there are some of the journals have already started making those changes, but I think it's necessary, because we can't go increasing the numbers infinitum.
We do have somebody from the publishing world, and who's also a faculty. Prashant Kamat is in the call, so I'm sure he's listening carefully. I think
didn't he have a commentary recently on exactly, he chose some of his favorite superlatives on some unfavorite titles. So if you haven't read it, do read it.
Yeah,
I totally agree with Alex and Feng about, like, when I read papers, I don't care about the metrics. I want to see what you learned in the fundamentals. And to me, that is way more interesting than like making something, 2% better. And now you have the, that's actually how science moves forward is sort of with the fundamental knowledge. And I also say this, I don't think there are as many people in homogeneous electrocatalysis here than maybe heterogeneous, but the metrics are quite different. And I think that if you do want to compare the two, it's worth understanding the differences. Homogeneous catalysts don't have traditional Toffel plots because we have different density of states. And so we sort of turn on or turn off at redox potentials. And I think sometimes in the past, when people have tried to benchmark or compare, it's quite different, and just sort of understanding the differences is useful, because I've seen people make these assumptions about it that are incorrect. I think Mark Robert is probably one of the people that has led sort of finding ways to standardize homogeneous electrocatalysts in terms of metrics, which I find very useful.
Okay, Aleksandra, let me just go quickly to a question from Arti, because it's very much appropriate to the discussion we're having right now. So I apologize that I'm going to push you just once more, but I promise I get to you. Arti, why don't you bring up that question? Because I think it's a really important question in the context of what we're saying right now. Arti?
Yeah, hi, can you hear me?
Yeah, we can hear you.
Yeah, okay. So thanks a lot for allowing me. So just following on these numbers, what I have usually heard is like, you have this number and you have to beat the Faraday efficiency of, say, CO2 reduction reaction. You have to get this number higher. And that is the only chance that you have to publish in a good journal at the end of the day. So my question is, does that really not influence where you publish at the end of the day? As everybody says to you that you should publish like X number of papers in these journals to kind of actually have a career in science at the end. So, and I've been told otherwise. So being really honest, I've been told otherwise, that you really need to have a good number. You really need to have very good publications, and then you can kind of think of a career ahead. I'm sorry, but being really frank, that is how I wanted to put it out.
I absolutely love that you're saying that, and I hope you bring it up again on Wednesday in the publishing panel. Any takes there, the romantic view of the scientist versus the real world, how things work, in reality. Thoughts there?
I guess in the end, I don't know what your goals are. I know some people are interested in faculty positions, and I've been on many search committees, and if someone came in and gave a research talk where they were like, well, we just made something better, and without a lot of insight, we would not be that impressed. Of course, we're a chemistry department, not an engineering department. So we really want to know the insight. And if you could explain that well, then that's more important than papers in journals. But that's my point of view.
If I may add to that, because sometimes it is, you might discover why something is not working, which means your numbers will definitely be lower than anything out there, because you know exactly why it is not working. And I think the insight is the thing that most value. So even if you are claiming that you have the highest number on the planet for whatever that you might be targeting, you still need to have a hypothesis why this is working, and you still need to have a plausible explanation, right? So it is not only, yes, we talk about jokingly about superlatives only, but you still need to have a hypothesis why. So if it is, the error margin in my, geometric surface area is 5%, and my metric is 5% higher, whatever the correlation might be, that is not feasible, and it should not really be published, right? That should be up to the reviewers and the editors to make that judgment. So I think it's also a question of, so the insight has to be there in some way or the other. So talking about errors is something else that the community is not very good at in general, right? What are the error margins? What is the reproducibility? Feng pointed, like, I would like to make this in my lab before I trust it. Just bringing that up.
Just to kind of give it a context, I've been working on copper. It has turned out to be really interesting because apparently everybody knows it's electrochemistry, but nobody knows how the CV actually looks like. So we've been working on the fingerprints. How should a copper single crystal, like not any copper, a single crystal should look like? And then when we were trying to probe that, I would not like to name anybody, but it was like, okay, if you probe that, it's like, fine, you get something out of it. It is an insight, because that was afterwards used by a lot of other researchers to prove or to kind of indicate that they have something like this surface now. They just don't have a copper. They have a copper that looks like 111 more than a normal copper surface. However, we were kind of pushed towards publishing it in a journal that might be a slightly lower than, the one that I wanted to kind of bring it up into. So that's kind of from a personal context that I'm putting it. It's because sometimes you're not even allowed to kind of go out there and kind of explore that there is a possibility. If I say that I do this like this, and there are people who were actually able to reproduce that, which was for me the best reward than any other impact factors. But I'm like, this should be somehow rewarded. Like, it's not just my case. In general, I feel happy if somebody could kind of back it up and then, have a good scientific discussion on that rather than numbers at the end of the day. So just wanted to bring it up.
Thank you for sharing. I think this is really, really important. And you bring something up, like there's been an inflation in all aspects, including science, as you bring up, like the impact factors. But in the end, the good science pops up to the surface. So if you truly find something that is really, really important, it will get cited. You might be ahead of the curve. As I mentioned, the platinum and ORR example, it was not published necessarily in Nature or Science. It was published in a lower impact journal, but it is cited extremely, right? It's also single crystal work. So everything has its place. Don't get obsessed, I would say, with the numbers. It is, if your work is truly impactful, it will show itself beyond the impact factor numbers, basically, right? So, but being ahead, doing state of the art and ahead of the curve can feel daunting, because some individuals might not realize that you are onto something, right?
Right. Yeah, I agree to you that it's then like it is dependent on the individual to kind of take that fight. I will put it that way, take that fight themselves. But I would appreciate if there is a little bit help from academia or publishing or people who are actually in power to kind of make that as a culture. So
I will say that what you can sense from what you're hearing is that it affects them too, right? JiaBin, Alex, and Feng go through the same game.
So I fully understand what you're just trying to argue. This is once it's become a culture, it's become a little bit difficult to reverse it. It takes some time to go back. If you look back at the electrochemistry back to 1990s, for example, those top ones don't publish in Nature Science. Okay,
yeah.
Top articles. Electrochemical Society is the #1. Used to be, at least. So I have to put it this way. But I understand your point. Nowadays, if you're trying to get an academic job, right? If you have a bunch of Electrochemical Society, maybe put you a little bit of difficult position compared to if you have a bunch of Nature Science. Let's just be realistic, okay? But it's hard to reverse that, I have to admit.
But there's a possibility. That's why I'm bringing up here. Like, now you guys have the reign to kind of change things. And if you do that in your own groups, then
I would say back to your original comment on performance versus fundamental insight. I would say a solid scientific paper need to have a solid scientific insights. Okay, that's the #1. Of course, on top of that, if you have a great performance, that's of course it's better, right? Combine these two together, that will be a strong paper. But without any scientific insight, that's really not a scientific paper, okay? I have to put it this way. So you kind of can judge it. Every reviewer have their standards to judge it.
Okay, I'm gonna move the ball because we'll come back to this issue, and it's a point of grief of all of us. And so we're gonna go to a question now for real by Aleksandra. You have the floor.
Hello, I love where this discussion has been going. I'm very fascinated by the concept of superlatives, and I have definitely seen a lot of papers where, yes, this is 2% better because you barely change the ligand scaffold, or in a heterogeneous system, something like that. I have a question about cell design. How much of an effect do you think that cell design has on the electrocatalysis outside of the actual catalyst? And specifically for Aleksandra, is there a way that we can model and think about this to make the most efficient system?
So I'm not an experimentalist by any means. I'll let Feng and NGenE comment on the overall cell design errors, pitfalls, etc. But from a modeling perspective, I mean, I would say we're quite good at modeling, the individual components, and then it's really the interfaces, which is basically what you obviously need to model the whole system. A lot of people talk about the holistic approach, basically studying the system as a whole, not its individual components, right? So I think that's kind of where we're heading. I mean, there are attempts where, we can treat things not at the atomic scale, but at a more classical level. That approach does not always capture actually the chemistry taking place at the interfaces. So there's like a trade-off and a lot of development, model development that needs to come into play. As of now, it's been the individual components that have been optimized, not so much the interfaces. I would say that if you look into the physics community, for example, they have been talking a lot about heterostructures. They've been talking about superlattices, et cetera, where it is very important how what is the cohesion, what is the adhesion between the two components. And I think that we can learn a lot from that. And then, at the cell level, I'm not an expert there. I'll bounce that to Feng and NGenE to talk about that.
Okay, it's tough. Probably reactor design is the most tough things you have to encounter in electrochemistry, I think. Because as I mentioned in the opening remark, it's not just a catalyst. You have so many things going on, right? So I can name a few of them. You probably already look into it. Flow field. Serpentine versus parallel, just a simple change could change a lot of things. And how you operate on, what kind of a membrane you put in there. Do you do MEA or do you do other configurations, right? There are so many ways to operate a cell. You flow liquid supporting electrolyte without the liquid supporting electrolyte. And if you feed a gas feed into your system, if you're doing CO2, let's assume that case, you probably feed a gas phase CO2 rather than dissolve in the aqueous liquid in order to achieve a higher current density. That could make a big impact. And also reactor design also including other things like whether you operate the systems in acid base, particularly for CO2, the community now reached some kind of consensus. If you operate in base, you're actually going to lose a lot of CO2, right? Then you're dealing with how to recover the electrolyte, how to separate the products, those kind of issues. So the bottom line is to design an efficient system, it's not, there's no simple answer to it. So how to start with this? This is what I'm trying to get to. So modeling definitely helps, but I don't think at the modeling level, you can model the whole system because it's just so complicated. But we can start with simple ones like a transport modeling to look into iron or mass transfer across the membrane, for example. This is something we are doing. The other things you can do is how to measure things properly. For example, if you put a cell together, a whole cell, you talk about cathode, anode, membrane, right? Basically, that's three major components. Do you know the voltage loss for each of the components? Usually we don't know. We just measure, say, hey, the whole voltage is 3 volt or 4 volt. You just report that. And most of the time, people don't know which part contributed to that 3 volt or 4 volt. This is another kind of things I think the community don't do that well at the moment, is to measure things properly and accurately. Then you can identify what's the limiting part of the system. then you can design it in a rational way to improve it. Then you can improve the overall performance. There's a lot of work need to be done on that end. And to be honest, we are still at the very beginning and trying to learn more things. And for me, we learn a lot from fuel cell community. They have a lot of experience design fuel cells very well. Of course, some of the knowledge cannot be easily transformed into the CO2 electrolyzers, unfortunately, because they don't dealing with the same resistance as we dealing with CO2. So there's new knowledge need to be generated. So that's my comment on this.
You know, related to what you just said, since you were talking about the way that you get the CO2 to the reaction, there's a question by Jordi who has mic problems. I'm going to read it. Saying sometimes people use concentrated bicarbonate electrolytes to generate in situ CO2 by using a bipolar membrane. And then that CO2 is converted to products on the catalyst interface. He would like to know what you guys think about the challenges of such experiments, such as the role of the catalyst or the effect of pH. Any comment on that?
If you use a bipolar membrane, the first question is how durable it is, how efficient it is. You have to talk to membrane community. There are a bunch of people doing that. It's not necessarily a catalyst issue. Membrane is a whole lot of issues actually, particularly bipolar membranes. But the challenge is also opportunities, right? So let's see a problem different ways. I think for a new generation, you're always looking for something is a challenge at the moment. If you can make some improvement, that's your thing.
That's a good way of putting it.
Yep.
Let me, we have a couple more questions and running out of time. So I'm going to try to run through both. Are you able to unmute yourself?
Yeah, can you hear me?
Yeah.
Yeah, this is just a general question for all of you, because my background is energy storage, not the catalysis, and I'm also experimentalist. I work on AFM. So there's the problem or questions you describe for this catalysis is really vast in terms of time scale, spatial scale. It's very complex. Do you think AI, artificial intelligence or machine learning can help to solve this? As you know, doing a lot of experiment is time consuming, computer time, modeling is consuming. Do you think, how do you think this general push towards machine learning and AI might help in catalysis field? And if you do think they help, which specific aspect you think they might have the most impact in terms of, for example, predicting materials or intermediate, or like which aspect?
I would say it's a great tool, as many other tools that are available. I don't think that it's the single answer to all of our problems. So I think we should be viewing it as a powerful tool. It is a computational tool, so keep in mind you will not get it for free. It still will cost you time and produce some CO2 as any computational work, as we're always facing. I do think that the problems have to be quite specific. It has been applied in catalysis, finding new catalyst materials, as well as, in batteries, for example, studying stability and like lifetimes of batteries. In many cases, it has so far depended on quite some data. There are new models where smaller amounts of data, doing things on the fly, and letting the ML models learn and target and guide you where your next exploration will be. I think that's kind of where we are currently. I think it's a great tool, but I wouldn't say that it will solve everything, which it is sometimes treated as, basically. I think we're like the scientific community is very different from, some of the big corporations that are using it just by us clicking and collecting data on us, right? But I think it's awesome, and we can use it much more than what we have. So I think we can see speed ups in the computational model, everything, from density functional theory to molecular dynamics to classical models, et cetera, et cetera. That's at least my take on it. And we can also use non-experimental data, very important, which I think is one of its beauties.
We have one more, and I'm gonna insert it here. Joy, do you wanna unmute yourself and ask your question?
Yeah, thanks, Jordi. Yeah, so I had a question. I think we touched on it a little bit earlier, but as we begin to develop more complex models, the different things happening at the electrocatalytic interface, even for like model systems, there's a lot going on with absorption and electric fields, etc. How do we deal with things like data insufficiency and overfitting? And I know this is kind of a personal question, but like as you navigate the approach between overfitting things and like getting too into the weeds versus having a model that's too simplistic, like how do you strike that balance in your research?
Certainly in our systems, I think Jordi said it this morning that like just because you measure a current, you know, what's the current from, right? And in the end, as I always tell my students, electrochemistry is one tool, right? But we have many tools, and so we need to also back it up with, you know, certainly in our systems we have a lot of spectroscopic tools. We can independently synthesize some intermediates and look at how they evolve separately, or and what their properties are. So I'm a big proponent of like, you know, we cannot rely on just electrochemical measurements alone to do these types of analyses, because they're, as you said, you know, if you have enough variables, you can fit any data, and we don't really know what's going on. And as much as I love electrochemistry, it's not powerful enough of a tool at this point to answer all those questions.
You will hear more about topics of machine learning as the week unfolds. We have a panel on corrosion on Thursday that happens to put together a number of people that use machine learning tools for that purpose, but you might see some generalities there that will come up again. Okay, so I don't know if you've noticed, Jenny, Alex, and Feng, but there's been a little bit more discussion in the chat, and this topic of you know, record breakings and, you know, what it takes to publish in certain journals has really hit an important point for the students, which is an interesting development of this panel. So I'll make sure to keep this conversation alive as we move on, especially since this year we have publishers that are going to be discussing their takes. This topic will come up again. On just one parting thought on, since I have a minute, on the question of cell design, are you aware of any papers, again, that attempt to kind of convey benchmarking efforts when you're studying certain you know, phenomena in electrocatalysis? You know, use cell A if you're more interested in, you know, charge transfer kinetics, or if you're more in the design of mass transfer, you know, work on this other space. Are you aware of efforts like that in the catalysis domain that they can go and look and read?
In CO2, I don't think so. Everyone uses slightly different cell design, which I think is a good thing. To be honest, I feel that's actually give the room for more creative thoughts on ideas to grow, rather than at the very beginning just standardize everything. Oh, you have to measure it this way. You know, it's not like a fuel cell community have been developed for so many years. Then you have to benchmark your catalyst carefully. For CO2, we are at the very beginning. So I will say, why not just let those creative people do their creative thing? That's my personal opinion, of course.
Mm-hmm. Yeah. I have a comment on this because I am a synthetic chemist and did not originally do electrochemistry either. And in our CO2 capture project, I started working with an electrochemical engineer, Vic Bruchette at MIT. And that has been tremendously useful for me because, and actually working together. So, you know, instead of trying to do something in isolation, think about a half reaction or something, you sort of think about the whole cell and components and what are the requirements. And we just learned so much about, you know, solvents and concentrations and, you know, and he's working as well as his colleague Alan Hatton have published on how different cell designs how to calculate energy efficiencies from different cell designs. And I just feel like if you are, more on the fundamental side, working on a catalyst to work with electrochemical engineering, because you'll learn a lot about sort of the different requirements of the whole system that maybe you wouldn't have thought about otherwise.
Yeah, so that's also a very good message for those of you that are younger. I mean, you don't have to do everything yourselves, right? You can, once it's time to think about benchmarking, then you can find partners, and you have some people here that you can contact that have experience, with the numbers. And sometimes it's easier to, we do something similar to what Jenny says, as we're a chemistry group as well in a different field. But there's a point where we say, now we have to let people that do this for a living evaluate and see if this is going anywhere. And that's perfectly valid. You don't have to beat everything yourself alone. Okay, so on that interdisciplinary note, we are just above 2:30, and I promised that I wouldn't take more than 90 minutes. I don't want to burn people on the first day. So I'm going to go ahead and conclude the panel. Thank you, Jenny, Alex, and Feng, for sharing your thoughts. Very candid, especially when you were, probed on the context of publishing, which, it's something that we all have to deal with sooner or later. Thank you for those of you that have contributed to the discussion. Those of you that are there, keep your questions coming. We have a little bit of a break. This one is shorter because at 3 p.m. we start another panel. We start our last panel of the day. So go and refresh yourselves, and